Can I share my screen?
Sir, not now. We'll just start with a brief welcome and followed by a keynote address, and then you can share your screen.
Okay, thank you.
We are audible, sir?
Yes, sir. Yes, sir. Very well.
The seniors and officials from PCRA, Ministry of Petroleum and Natural Gas, Executive Director, CSPA, Risk and TQM, GAIL, Executive Director, Training and HR Policy, GAIL, and all my seniors from GAIL and dear friends, a very good morning to all of you. Like previous years, this year too, PCRA is conducting SAKSHAM under the banner for the year 2022. It's a flagship annual public awareness program campaign to urge the citizens to participate in mass for fuel conservation, for health and environmental protection. This is to help India to become self-reliant and to lessen the bills on towards crude oil imports. We are extremely happy and proud to be hosting and partnering today's event and joining hands with PCRA towards this mass awareness program jointly with PCRA and Ministry of Petroleum and Natural Gas. To start with today's program, let me invite Shri S.K. Guliani, ED Training and HR Policy from GAIL, to formally deliver the welcome note address.
Thank you, Aprajita. Good morning to all. I, on behalf of GAIL Training Institute, GAIL, welcome officials of MOPNG, PCRA, senior officials of GAIL, my colleagues and friends in GAIL, other officials from other sectors who have joined today this webinar. I welcome you all for attending this webinar on role of hydrogen as a fuel in sustainable environment. This initiative is a part of the SAKSHAM-2022, that is SAKSHAM-2022. I extend a special welcome to Professor K.K. Pant from IIT Delhi, who will be making us aware about hydrogen, its use as a fuel in transport sector, and its overall impact towards sustainable environment in the long run and taking care of the climate. I simultaneously take this opportunity to thank Professor K.K. Pant, who has accepted our invitation to deliver this webinar for the benefit of all of us and the masses as a whole. GAIL is extremely happy and proud in hosting this webinar, partnering with PCRA as a part of the celebrations towards Azadi Ka Amrit Mahotsav. As we all know, PCRA under the aegis of MOPNG is involved round the clock in furthering is involved round the clock in furthering the cause of energy efficiency, energy conservation while using various fuels in various sectors, e.g. transportation, industries, etc. As we all know, SAKSHAM is an initiative of PCRA, which is celebrated every year for creating awareness among masses towards energy conservation and energy efficiency. This year too, PCRA in association with oil and gas PSUs is organizing mass awareness campaigns towards fuel conservation, energy efficiency, and resulting impact on climate change. The theme of the SAKSHAM-2022 is Harit और स्वच्छ ऊर्जा अपनाएं, आजादी का अमृत महोत्सव मनाएं. Today's webinar is one such contribution of GAIL for awareness of the masses to understand the role of hydrogen as a fuel in sustainable environment. I welcome everyone to get maximum benefit out of this webinar, which is being taken up by Dr. Pant from IIT Delhi. Let's pledge to contribute towards green and clean energy for the coming generations. Thank you. Thank you so much.
Thank you, sir. Thank you for doing the honors of welcoming our esteemed speaker of the day and all our distinguished guests. May I now request Mr. Ashu Singhal, ED, CSPA, Risk and TQM to deliver the keynote address and set the stage for today's speaker, Sri KK Khan.
Thank you, Aparajita. A very good morning to Mr. Pant, the Professor Pant, connected through video conferencing, and all the participants. It's a live telecast, so everybody connected through the webinar, and also the GAIL employees were connected through the video conferencing. My colleagues present in the hall, Mr. Guliani. Thank you very much, Mr. Guliani, for setting up the tone. So this is an important occasion for all of us in the TQM department. We coordinate with Ministry of Petroleum and PCRA for this annual event, and also create this awareness session amongst all the people, including giving a live telecast to all the persons connected through the webinar. So this theme is Clean and Green Energy and Azadi Ka Amrit Mahotsav. PCRA is doing a lot of flagship events like Cyclothon, Walkathon, and other awareness campaign for conservation of petroleum products, because everybody knows that petroleum products are not going to last for long. That is one reason. And the second is the polluting impacts it has on the environment side. So there are two parts. One is the global warming and second is the local pollution. In India, we are facing a lot of hardship because of the local pollution. So that is also another important key factor, which is critical for determining the good livelihood and health for the countrymen and the citizens. CNG has played an important role, as we all know, in abating a lot of pollutants which were there in Delhi after that Supreme Court decision to implement CNG in Delhi and NCR regions, as well as shifting some of the polluting units out from NCR. So that has made a major impact on the type of pollutants which we were facing in late 90s. Now India is moving towards energy transition, including moving to net zero emission by 2070, as announced by Honorable Prime Minister in COP26. So for achieving that, many things will be required, including how to phase out petroleum products in a gradual manner, as well as to introduce alternate fuel, because in India, the per capita consumption of energy is very low, as low as almost 1/3 of the global consumption. So there will be definitely a lot of urbanization happening, a lot of people moving from low income to high income groups. So that will increase the energy consumption. But the good part is that we are yet to develop the infrastructure. So we should develop an infrastructure which is more sustainable, which is having least carbon footprint, and which can meet the demands of the countrymen. In that respect, Ministry of Petroleum is doing many steps and the PSUs under the ministry are also doing many things. Some of them is renewable energy. Many petroleum companies have given themselves some targets in wind energy as well as solar energy and other forms of renewable energy. Ethanol is being promoted from 8 to 20% in another 3 to 4 years by mixing ethanol and the petrol. Then compressed biogas is being promoted by government by mandating offtake of compressed biogas at all the CGD outlets, which will at some prefixed price, that is 46 rupees per kg. So that makes it a more viable option, and many entrepreneurs are putting their money in this project, and financing also is being done through government agencies. Now, one fuel which will be very helpful in doing or abating the hard to abate industry is hydrogen, because hydrogen is thing which can replace the direct burning of the fuel, which maybe electricity at some places cannot do that, like steel and refineries and some other places where no other industry, electricity cannot replace such a fuel. So hydrogen can play an important part in abating the pollution in those things. Now, in the recent hydrogen mission policy, which has been announced by government, some incentives have also been introduced, such as this interest rate transmission charges have been waived off for 25 years. Banking facility have been given. BGF fund has been announced for promoting electrolyzer manufacturing and other such elite services for promoting hydrogen in emission mode. Then there is green hydrogen consumption obligations have also been made in city gas, fertilizer and refinery sectors. which will be an important step to boost the use of hydrogen in the country. There are several pilot scale projects are being taken up by various PSUs. GAIL is also not left behind. We are doing many things. And the two major challenges which comes up in hydrogen is the transportation of hydrogen from the place of production to the place of consumption. So in that respect, we have done certain studies with Technip and EIL to see how much of hydrogen can be mixed in the existing gas grid. And in that direction, we have started one pilot project in Indore in the city gas distribution network. We are blending 1% of hydrogen. Recently, we have also floated an inquiry for 10 megawatt electrolyzer facility near Madhya Pradesh in Vijaypur, a place near Guna, which will be commissioned in another 1 year time or so. So this will be the first of its kind in India, at least, for 10 megawatt capacity and maybe the second largest in the world. So these are some of the important initiatives which we are taking, besides exploring several others with our joint venture companies and other things. So when we talk about the energy transition of the country, we will find that there are several things like affordability. Then there is job security of the existing fuels, which are giving job security to several people in the country. Then there are resources available in particular country and the region. Then infrastructure creation and new infrastructure creation for the new type of fuels or alternative fuels. Then affordability, environmental impact, and sustainable development. So these are the important criteria to determine how we can transit to a new fuel module or mechanism by having least impact on the environment and at the same time ensuring the accessibility and affordability to the people here. So in this respect, I think today will be an important day and we look forward to Professor Pant's address in this important subject of hydrogen, how it will act as a clean fuel for the coming economy for the country. In this respect, I would like to end with few questions to Mr. Pant also, like there are certain advantages of hydrogen, which is not there's no doubt about it, that it can abate certain industries which cannot be done otherwise. It can integrate with renewable energy, because if the renewable energy is 500 gigawatt and the peak consumption is not that, so that power or excess renewable power can be used to produce hydrogen and which can act as a fuel in future. And it is least polluting. There is no doubt about it. When renewed or coupled with renewable energy, there is no pollution with it. But there are a few challenges also with hydrogen. Some of them is the transportation of hydrogen from the source to the consumption point. And there are not many options available as of now. Second is the affordability of hydrogen, that currently it is very, very costly as compared to gray hydrogen or even with CCUS and other technologies or options available. And third is, if we go by electrolyzer, the water aspect of it, and how much of water will be required, the DM water which is needed for electrolyzer, and how that problem can be addressed. So I think, thank you very much for your patient listening, and I will hand over to Professor Pant to take it over from here. Thank you very much.
Thank you, Dr. Ashu, for a nice, I think, introduction. And it's a need of the hour, as you said, the hydrogen requirement for the future. And when we talk about the concept of green hydrogen, definitely, I think it's very challenging in terms of the storage, transportation, distribution. There are many things. So I would like to cover a couple of things during my talk on this hydrogen. So can I share my screen, Ms. Aprajita?
Yes, sir,
Yes.
you can share your screen now.
Okay. Is it visible?
Yes.
Yes, sir, visible.
So before we start the formal session, I would actually like to introduce our speaker to our audiences and our attendees here.
Yeah.
So let me take the privilege in introducing our speaker, who is a very, very renowned academician, and he is actually an eminent scholar also. He is presently the Petrotech chair at Federation of Indian Petroleum Industries. He is a Dean Faculty, IIT Delhi, Professor, former head and Department of Chemical Engineering at IIT Delhi. Besides this, he also serves as adjunct faculty and honorary faculty at universities in Canada and Australia. Professor Pant's academic and industrial research experience spans over 30 years with almost 180 plus publications, having 9,800 citations and numerous patents to his name. He has successfully completed over 50 high-impact projects and consultancies valued more than 500 million Indian rupees from premier companies and government organizations. He is among the leading academicians in India who is working on cutting-edge and futuristic technologies of national and international importance like coal to methanol conversion, e-waste and plastic waste management, hydrogen generation, CO2 capture and conversion, biomass valorization, etc., using catalysis and reaction engineering. All the topics are so very relevant and pertinent to GAIL's business areas. He has also delivered several talks at prestigious platforms and has performed editorial roles in several journals of repute and has held several administrative positions in IIT Delhi as well. Professor Pant has been conferred twice with the prestigious Gandhian Young Technological Innovation Award and also has several other awards to his name. So with folded hands, we welcome you, sir, and we invite you to this session on role of hydrogen and as a fuel in sustainable energy. Over to you, sir.
Thank you, Ms. Aprajita, for elaborating my citation, though that was not required. So a very good morning to all of you. And I thank Dr. Ashu for giving the introductory remark about need of the energy and when we talk about the clean energy, and that becomes a very important. So I thank MOPNG, PCRA and GAIL for initiating this activity and allowing me to give my thoughts on this hydrogen as a fuel in sustainable environment. So with some background, what already Mr. Asu explained about these things, that what happened in COP26 and then COVID pandemic and gradually the CO2 concentration, which is now around 410 ppb in the environment, and that makes the overall system very challenging. And already it has been said that by 2070 that it should be zero carbon. So how to do that? That's very challenging. And if you look at the data here, the carbon emission from all these burning fossil fuels, which has increased to 36.4 billion tons, which is around 4.9% increase in 2021 compared to 2020. So that's what the COVID impact has been seen here, which can be seen from there is a dip and again there is a continuous increase in the carbon dioxide into the environment. If you look at the India's carbon emission, that is also projected to increase by 12.6% this year. This will go to a level of 2.7 billion ton, which is approximately 7% of the gradual. So all these things, and India, already has committed a net zero emission by 2070. And you see the consequence of the increase the carbon dioxide in the environment, the temperature is rising, and because of this, there are several other complications that come up. So with this, there is a need to look at the non-carbon fuel based economy, and that's why we are talking about hydrogen economy, and I'll give a couple of glimpses of this, how this can be done and what are the challenges, and which were the question Dr. Ashu has already raised in the beginning of his introductory remarks. So you see that the fossil fuel demand, and when you look at the energy demand, it is increasing continuously, and most of this demand, say in India, 90% of this is from this crude oil or natural gas, And when you look at the temperature is increasing because say of this carbon dioxide into the environment, and which is approximately 1.5 degree, that is to be increased by 2033. So that's again a big challenge. So therefore everybody is talking about how to reduce this carbon fuel, Hydrogen could be one of the promising fuels, or energy carrier in future. Whether it is a fertilizer industry, refinery, petrochemicals, or maybe in the transport sector, right? The hydrogen could play a major role, and that's why the hydrogen is hydrogen-based economy is coming up in a big way, whether it is the different kind of feedstock, biomass, coal, natural gas, or some other sources. But there's a need. But the future is again not in terms of the grey hydrogen, what Dr. Asutosh has raised. It should be a kind of green hydrogen. So that's now the challenges are much more stringent in order to make this possible. So again, you see that the demand of hydrogen, right? Because it's one of the fuel which is widely used in refineries, petrochemicals, iron and steels, right? Chemicals. So everywhere you know the demand, and you see that demand is increasing continuously. So it's not a linear growth of demand of hydrogen, but rather exponential. And this is not including the transport sector, right? So that's very, again, because when you look at the application of hydrogen in transport sector, then this is going to be much higher. So Indian demand approximately in terms of these chemicals, right, requirement is around 6 million ton in 2020, and mainly it is for methanol, petrol refining and ammonia. You see the number again here, right? The refinery and the fertilizer industry consumes a large amount of hydrogen. That is what the current trend. If you go globally, the hydrogen, how is it produced? Because it is, I said, mainly it is being used by refinery and petrochemicals, not for the energy sector, or very limited fraction of this is being used by the energy sector. So you see that most of the hydrogen is being produced by the natural gas. So steam reforming of natural gas, everybody knows. A very small fraction, if you see 196 million ton of oil equivalent of natural gas, which produces around 69 million ton of hydrogen, right? And a very few fraction of that is through carbon capture and utilization. Because when you talk about the concept of gray versus blue versus turquoise hydrogen or green hydrogen, then this factor also becomes important, because if you capture the carbon dioxide, it will add to the the cost of the carbon dioxide capturing. So out of this, again, you see 38 million ton of hydrogen is consumed by the refinery, and 31 is around by the fertilizer industry. So that, and these are the small fractions which you see, which are coming from the different sectors like byproduct of hydrogen, right? So there are the numbers which are coming, but its fraction is very small. So if you look at the global hydrogen demand as of today is around 120 million ton, currently, and there is a continuous increase in the hydrogen, and most of the hydrogen which is coming from the natural gas. If you look at that, it is expected that this will grow by a number of 200 million tons by 2030 and 530 million ton by 2050. So you can see that what kind of exponential growth, in terms of hydrogen demand will be in future, if everything is being based on the hydrogen. This is a kind of speculation when you look at the hydrogen, because you are talking about in terms of the net zero emission, and then you see the fossil fuel with carbon capture. So this is the yellow one which you can see here in 2050. So around 200 million ton of hydrogen will come from this with carbon capture. This could be again a future if the cost is a major factor here. But this could be that most of the fraction will come through the electricity, that is where we are talking, or maybe the electrolysis of water. So those things could be a future approach for hydrogen production. But these are still the R&Ds are to be done in order to make this possible. So now you know that, already a lot of things have been done on hydrogen as a clean energy carrier and multiple applications. So as I told, the natural gas, is a main feedstock for hydrogen production, but everybody is talking about renewable energy sources. So geothermal, all these could be nuclear energy, could be one of the major source of this clean hydrogen when we talk about the green hydrogen, India has plenty of coal, So around 160 billion ton of proven coal reserves are there. So we need to look at this also as a source, but how to make it a green. It's not a green hydrogen, but how can you convert it towards the turquoise hydrogen with carbon capture? It is still lot of things are being done by Ministry of Coal in this regard. So that is also very important in future. So the hydrogen of course, right, it has a lot of chemical applications like petroleum industries, right, recovery and refining. So most of this is consumed by approximately 47% of hydrogen is being utilized by the refineries and petrochemicals. 4% of the hydrogen is used by the methanol production. So this is still a low number because very low amount of methanol is being produced in India at present, and mainly it is being imported from different countries. So that's again that the coal to methanol concept which has already been made, or the green methanol which can be from the biomass based feedstock. So that is again a demand for the future. The hydrogen is mainly consumed by the fertilizer industry for ammonia production. So 45% is in the ammonia industry, and these are the small, right, like the other industries where the hydrogen is being consumed. But this is the future where we are looking that can this hydrogen be used as a energy carrier for the transport or as a fuel? So fuel cell demand, engines and turbines, energy storage, all these things, right, like battery application. So these are where the transportation sector is looking in terms of the green energy, and then hydrogen becomes very important in future as a source of energy carrier. So everybody talks about the color also, because when we talk about the hydrogen, so it's not about just like the coal or natural gas reforming, and that gives lot of these kind of hydrogen, which is generally the source which you see, the coal or lignite based, by gasification process, you generate the hydrogen from there. But this is totally a kind of coal, that large amount of this is carbon. So it's a carbon rich feedstock which is to be converted to hydrogen. So what is the future of this carbon dioxide which is coming from there? So how to capture that? So that's a big challenge, and that's what the challenge in terms of the brown hydrogen that cannot be utilized in future. The second one, which is the gray hydrogen, and here we have the opportunities, the natural gas steam reforming, which gives around 13.6 kg of hydrogen, 13.6 kg of carbon dioxide per kg of hydrogen. So how to capture this to make it a kind of towards the blue hydrogen, So there can be the opportunities where this gray can be converted to blue hydrogen, There can be direct methane decomposition, which our group is working with HPCL. So methane decomposition, you have the carbon nanotube and hydrogen, and that could be a kind of where you can call it a blue hydrogen, Another one where you look at the in terms of the energy, because when you use this reforming, you are again using the energy either from the fossil derived feedstocks or maybe electricity. Again, if you look at the life cycle assessment, there are a lot of questions that how much is the energy input and which in that energy is whether green in terms of the efficiency. So again, the question comes, if everything is being done through like solar energy, wind energy, and then you are producing hydrogen, then it can be called a turquoise hydrogen. So here is again an example what we are talking, the methane decomposition or pyrolysis gives you carbon and hydrogen. Part of the hydrogen can itself be used as a source of energy for decomposition of methane, because methane decomposition requires large amount of energy, so around 550 degrees centigrade is the minimum temperature at which methane decompose. So if you want to have high conversion, it should be done at around 750 degrees centigrade. So how to utilize that carbon and that hydrogen which is coming is a kind of turquoise hydrogen. But at the end, everybody is talking green hydrogen, where you can use the renewable energy sources. And another more important is the electrolysis of water and biomass gasification. So biomass gasification earlier it was not considered as a green hydrogen, but later on, because if you look at complete life cycle assessment and carbon dioxide capture and convert it into value added product, then it becomes a kind of green hydrogen. So this is a very important challenge, that how to convert these all kind of hydrogens into a green hydrogen, which is the demand for the future. So why we are talking hydrogen, need not to talk much on this, but everybody knows when you talk about the green hydrogen, when you use it as a source of energy, it is just water. So unlike the other diesel or gasoline or other kind of the carbon based feedstocks where you have the carbon dioxide and several other impurities, and which pollute the environment. So that is where the hydrogen produces energy and water, and it is around 120 megajoule per kg, of hydrogen that can give the energy. So highest in terms of the energy density also, So that's a very important factor with respect to the hydrogen. It doesn't generate any carbon emission, talk about the hydrogen for the low carbon products, so hydrogen can be used because wherever you have the high hydrogen to carbon ratio, and if you introduce more and more hydrogen, then this is also important in terms of the chemical production, right? That's very important. So that's why the hydrogen is very, very demanding. In general, when you look at the emission point of view or when you look at leak point of view, so hydrogen is a safer fuel, right? Compared to LPG, natural gas, gasoline and diesel, but there is a lot of debates on this point, right? So when it leaks, it directly goes to the right at high concentration, but you know the explosive, right, between 4 and 75% concentration, the hydrogen is very explosive. So that's a big challenge when you use the hydrogen in the vehicular application. So that's one needs to find solution, right? The chemistry is very simple. And so this is where the hydrogen has come in picture. You see that if you can have the water electrolysis, you can have a tap, you can have the process by which hydrogen can be produced, and then you can drive your car. And that's what the vision for the future, or a kind of right speculation for the future, which one needs to do. So hydrogen can be used as a clean energy carrier. You see that it has the highest, right, carbon-free energy. So around 33.2 kilowatt hour, that is the energy is compared to the any other energy source. So that is the high number, and 30,000 kilocalorie per kg, which is approximately 120 megajoule per kg of the energy. So 1 kg of the hydrogen in terms of cleanness, if you see, right, it is equivalent to 7 to 8 kg of the coal. Right, so equivalent, and where we are talking without associated with the carbon of coal, and it is also approximately equal to 3 kg of the natural gas, or approximately 42 normal meter cube of compressed natural gas. So that is where the advantage in terms of the mass wise or volumetric wise, the hydrogen. Although the volumetric wise, this number will be a big challenge, because when you look at the kind of cylinder, the pressure which you need to store that much hydrogen, it's a challenge, and that is again where a lot of right R&D is being done. So hydrogen can be utilized, whether right you see it can be extracted from water, right, or from the hydrocarbons, fossil derived feedstock. It can be from the biomass also, right, but again the challenge. So a lot of R&D is being done in coal to hydrogen process and biomass to hydrogen process by capturing the carbon dioxide through this. So like electricity, this is also an energy carrier, and this is much more versatile due to its better conversion efficiency. So I'll discuss that part later, the efficiency of the hydrogen combustion. But in total, when you look at the utilization of hydrogen, it is a cheaper renewable energy, right? And hydrogen fuel cells are pushing hydrogen to central stage at future end. So a lot of research is being done in the fuel cell, right, demand. So 5 kilowatt right based fuel cells, right, or PMFC type fuel cell, where the methanol can be used, and methanol can be act as a hydrogen carrier, right? So that's what those things are. Or simple natural gas can be reformed, provided the hydrogen can be captured, carbon dioxide can be captured by using separate technique, and hydrogen can be used for the fuel cell application. So those kind of the plate former, right, what you call plate and frame type heat exchanger, and you can have the reforming, put a membrane, so carbon dioxide will go on one side and hydrogen can directly be used in the fuel cell application or directly in the IC engines. So the major application wise, if you see, when you talk about the hydrogen, right, I already discussed this part, but what I am talking about as an energy carrier, right, the hydrogen in the form of electricity and several other applications. So you see that these are right fuel based production, whether it is a methane reforming, biomass, coal gasification, the hydrogen. This hydrogen can be used to power, so fuel cells, hydrogen turbines, and combined heat and power cycles. So this can generate electricity, right, and then and power to hydrogen. So this is a kind of complete cyclic loop here. So when you look at the concept here, so we are looking at kind of green hydrogen, where the complete this cycle, and thermodynamics is very important when you look at the exergy analysis in it. The storage of hydrogen is again, right, the pressure vessels are to be used for hydrogen storage. This can be used in the industry, like right direct in the reduction of iron, and all these are also coal instead of coal, right, coal to hydrogen, and directly can be used here in the steel industry. Fuels, right, like in fertilizer, methanol is coming up in a big way. So hydrogen is required, CO2 hydrogenation also it is required, CO hydrogenation it is required. So syngas to methanol, dimethyl ether. So those things are again a kind of energy storage devices, or ammonia is also a green form of hydrogen storing devices. And this is where the future, right, how to utilize hydrogen in transport like cars, trucks, buses, trains, and the marine applications also, where a lot of R&D is being done, right, in shipping and aviation. So there are plenty of applications of hydrogen in terms of its advantage, but there are a lot of challenges here. You see here, this is the advantage, right? As an energy carrier, the gravimetric energy carrying capacity of hydrogen is around 33 kilowatt hour per kg, compared to, you see, natural gas is only 9.3. If you see gasoline 11.62, coal 5.23, biomass 4.2, and battery is still low, that is only right in terms of 0.25 kilowatt hour per kg. But the challenge is when you see this utilization, you see, we would like to have 100% efficiency, but nothing is available as of today for this 100% efficiency, right? And if you are able to do that, right, the specific carbon emission is quite low, only even less than this 0.31 kg per kilowatt hour. That is when we talk in terms of energy. But this is need to be done. Similarly, with 80% efficiency, if you want to run this engine with 80% efficiency, this is also not available as of today. And there the carbon consumption. So if you look at from top to bottom, right, where IGCC plus FC, right, you see these are the mature technologies, but the efficiency is only 50% here, right? And here the carbon, specific carbon emission is 0.63. So if you look at the last one, right, or this kind of, right, where you talk about the steam cycles, right, then the or supercritical cycles, then these hydrogen, right, if you are producing hydrogen, but efficiency does 35%. So 65% of the energy is going as a waste. Right. So the new trend should be, when you talk about the low carbon footprint, we should reach to these levels. Presently, unfortunately, no technologies are available at this point, but this should be the future. Right. Most of the technology have reached to a level of 60%, and even the improvement can bring to a level of 75%. Right. But after that, nothing is available. So that is where we need to work on hydrogen based fuel cell power generation, which delivers, right, lowest carbon dioxide per kilowatt hour. So fuel cell generally they do not have any limitation of steam cycles and complexity of ultra and advanced ultra supercritical cycle. So these kind of devices can be used in future. So market demand wise, if you look at, right, the coal, if you look at crude oil, natural gas, right, these all are the, right, feedstocks or fossil derived feedstock for the hydrogen production. If you look at the demand in terms of oil equivalent, so coal demand is around 430 million ton per annum of oil equivalent. Crude oil is 250 million ton per annum, and natural gas is 130, right? But when you compare it with respect to hydrogen, right, this is the current demand. If you fulfill the demand by green hydrogen requirement by replacing all this, only 143 million ton per annum of hydrogen will be required with that. For crude oil, 250 is equivalent to 53 million ton per annum, and this natural gas is 50 million ton per annum. But you see that right hand side, the extreme right, how much carbon dioxide can be saved if hydrogen is used as a fuel. So this is a huge number. So 1,625 million ton per annum equivalent CO2 saving due to the replacement. So that is where we are looking for the future, a net zero carbon emission. So it means from all these kind of feedstocks, either the carbon dioxide has to be captured efficiently and converted, or you go to these hydrogen sources which can directly replace these kind of fossil derived feedstocks, and then this can be a concept where you see net zero carbon emission. So this is still a hypothetical number which is written here. If the current demand of all the fossil fuels like crude oil, coal, natural gas, if it is replaced by hydrogen, you need around 276 million ton of hydrogen, right, to complete whatever the industrial and whatever the demand for the chemical production. So that is a challenge for here to 2035, right, how the carbon dioxide can be captured, and finally to a mission of 2070 where it has already been decided for net zero carbon. So now when you see that, right, the energy utilization in terms of hydrogen production. So hydrogen fuel cells delivering highest efficiency from the fossil fuels, right? So that is already everybody knows this part. So hydrogen from renewable plus fossil plus biomass will power the home around 1 to 5 kilowatt school. So these things are already being developed and have been developed. But efficiency, you see here, it is 50% fuel cell efficiency. There is a need to boost it to 75% efficiency, which I said. So 50 to 60% is available. But this is important because we are talking about the clean energy, we are also talking about the energy saving, like and a lot of things are to be done. So you see here, right, different kind of feedstock like methanol, biomass, right, all these are used as a feedstock and used in a reformer. We produce the hydrogen and that hydrogen is used for the fuel cell stack. It can be AC type or DC type. So 50% is the efficiency of this kind of cycle, which is already being done, right? But what I'm saying here, or what we are proposing here, all this methanol from coal plus hydrogen, which is coming from renewable feedstock, whatever the reject here, because 50% is rejecting here, that heat should be absorbed by vapor absorption machine, heat pump, and then again sent it back to for some other purpose. So with this, the additional 75% efficiency can be recovered. So that could be in total 75% efficiency of the combined cycle. And that should be, I think, the target for the future. So that is where these fuel cells needs to be, right, with improved efficiency. So that is to be done in future. So lots of things are there, right? If you say what is the present scene and what is the future to be done. So future is with hydrogen, right? And for all application, instead of using this coal, natural gas or biomass, right? So we have to look at, right, all these, whether the electricity grid, heat network, everything should be driven by the hydrogen in future. So that is where we are talking about long distance transmission and distribution systems that leads to loss, how these losses can be minimized, large size refineries which manufacture the liquid hydrocarbon fuels from the crude oil. So that is to be minimized. Battery, lithium ions, right? These are also coming up in a big way. So a lot of electric vehicles have come, right? So that is again, right, when you see the efficiency wise, it's there are a lot of challenges with that. So many critical elements, right, because the lithium is not available, right, and this is available in selected countries. So we need to find out the solution for these along with the hydrogen production. So why to use this, right? And what are the drivers for the hydrogen production? That's very important because see, we are talking about hydrogen energy, but where from this hydrogen will come? How this hydrogen, right, can be produced as a clean hydrogen or clean hydrogen, right? Then storage and transportation is a big challenge. Distribution of hydrogen is again a big challenge. So these are the major, right, kind of challenges to be addressed when we have to utilize hydrogen as a future energy carrier or energy source. So you said that the hydrogen production presently fossil and renewable. So both should be used. We cannot say that only water electrolysis will work or only biomass will work. We have to look at the fossil demand also because these are available in plenty. The only thing that how to make it clean is very important. So that's what we have to find out. This is a big challenge. In fact, when you look at the hydrogen production, one thing is that simultaneously utilize it, but utilization, if they are like in a power, right, or electricity grid, you store the power electricity, right? So in the similar way, the hydrogen, there should be the devices for storing the hydrogen. So hydrogen storage, transportation, so both at pure form or at its carrier. So ammonia could be one of the, right, hydrogen carrier. Methanol can be one of the hydrogen carriers. So those things are also important. And then application of hydrogen, whether it is for stationary application or mobility, mobile applications, or direct or indirect. So all these things are drivers for hydrogen energy as a source in future. So best pathway is to be chosen, right, and develop a policy framework accordingly. That is where all these, right, energy sectors or right, they have to work with the, right, development of these kind of policies, and couple of, right, organizations are already working for this, and hope we will have a solution for these kind of. So briefly, I will cover certain points, right, on the hydrogen production, transportation, and storage. So this is what you see the production challenges. Everybody is talking about green hydrogen, right, a decarbonized energy. So this is a green hydrogen by water electrolysis, right? But it's still a dream. It has not come to, right, to that level because the cost and other factor or energy factors are very important. So we'll discuss that part. Natural gas steam reforming is well known, right? So there is no issue, and this is a gray hydrogen. So already these color codes have been defined. Coal is a, you know that it's a kind of the hydrogen which is a brown hydrogen. Nobody would like to go with this. But if you have to find out coal gasification and then carbon capture and storage, and you can reach to blue hydrogen. So a lot of R&D has already been done in this direction, right? So already coal to hydrogen or coal to methanol, these kind of gasifiers designed, right, with the hydrogen to CO ratio, high hydrogen to CO ratio, and then again the carbon dioxide capture. So those things are being done. So Ministry of Coal has already taken lead in this direction also, and couple of this coal to hydrogen projects will come soon. That's one thing. So, and finally, the electricity from grid, right? That is again very important, that how to produce this electricity from solar, wind or other devices and generate the electricity, and that can be used for the hydrogen production. So that's again a future direction. So these are the couple of areas, right? But we need to find out the options, right, which can be integrated in the hydrogen economy, and that's very important. So all these processes are very important because it depends on the availability of the natural gas and coal, because India has available coal resources and these can be utilized for the hydrogen, but carbon dioxide capture is very important. So routes of hydrogen production already known, right? So methane reforming is well known. Then biomass, right? That is biogas CNG that can be cracked. Again, you can have green hydrogen from here. Carbon dioxide is to be captured. Coal gasification, lot of R&D is being done, right? Followed by water gas shift. You can convert coal to hydrogen. Bio-oil reforming is a green hydrogen. So biomass, you pyrolyze the biomass and convert it into bio-oil and reform it. Or biomass, you gasify the biomass and convert it. So both options are available. Again, the energy analysis for this is to be done. This can be converted to methanol, and methanol can directly be used in a fuel cell, or you reform the methanol, and that is a kind of onboard reformer. So 5 kilowatt to 10 kilowatt, these kind of reformers are already developed, right? So that is again a new, right, where the development in terms of R&D and commercialization. Then water electrolysis, right? That these are the kind of deal bed. These are the areas where the lot of things are to be done. And biological routes are again, right, which are kinetically slow, but these can also be used for hydrogen production by using the enzymes or microbes, right? And but the production is slow, so kinetics is very important. So those are also can be done. So this is where the renewable energy and fossil energy both are used as a source, and water splitting may be a new area. That's right, using the nuclear sources and split the water and generate the hydrogen. So when you look at the hydrogen production, right, or hydrogen utilization, that needs a 360 degrees of hydrogen deployment. So all these kind of, right, refineries have to come forward. The fertilizer, steel industries have to come forward, right? So industries like refinery, steel industry, chemicals, caustic soda, methanol, industrial heat, right? All these have to come forward. And then like fertilizer industry, urea production, right? Hydrogen is used widely, ammonium nitrates and this. So natural gas based hydrogen versus, right, ammonia can be used as a source of hydrogen also for storing the hydrogen. Gas economy, so blending with the national gas grids, right, all these, right, the grids based networking for electricity generation. Transportation is very important. When you utilize the hydrogen, so fuel cell based, right, hydrogen based commercial vehicles, trains, aviation, shipping, and power, ammonia, seasonal power. So that is where we need to look at a kind of 360 degrees shift, right, in terms of the hydrogen utilization by industry or transportation sector. So this is where the hydrogen is, right, currently when you look at the development in terms of value chain. So hydrogen from steam methane reforming is already well known. Coal and biomass, right, that is also be used. Chlor-alkali industry, hydrogen from water electrolysis, but lot of things are to be done here when you talk about the green hydrogen. Storage, compression, transportation and dispensing system. So that is important and is a challenge. Then hydrogen to energy via fuel cell that focus on mobility, right, system for, right, heavy vehicles, commercial vehicles, hydrogen boilers, heaters. So how to utilize that hydrogen energy is important. How to store the hydrogen is big challenge. So composite cylinders like type 3, type 4, couple of cylinders are already developed, right? But carbon based, composite carbon based cylinders are lightweight materials and these can be used for hydrogen storage. Then hydrogen to liquid fuels via carbon capture utilization, or ammonia reformer technologies, all these are very important. So what I mean to say, though these all are right important in order to utilize the hydrogen as a source of energy, because these are not developed yet, right? All these things are still at R&D, and couple of the multinationals have done some commercialization, but still it is to be come up in a big way. And in India, we need to do a lot of R&D in this area. So methanol generally is being utilized. So already a lot of things have been done. So this is a kind of R&D and some energy analysis. A methanol from carbon dioxide, right, is a hydrogen carrier, and compare should be pure hydrogen versus methanol as hydrogen carrier. So methanol versus hydrogen. So you see that you have a kind of 55 kilowatt hour renewable power, suppose, right? And this can give you a renewable power. So 1 kg of hydrogen has around 33.2 kilowatt hour of energy. So that's right. So one can calculate how much hydrogen is required for this. And this hydrogen can be pressurized and transported. So generally it needs to be compressed around 600 bar. So this compression will require around 2.8 kilowatt hour per kg of hydrogen compression, right? And then you are transporting it. So transportation with this, if you get this 1 kg hydrogen, 33.2 kilowatt hour of energy, the efficiency of this cycle energy output divided by energy input. So this is the energy which is consumed, and energy input is 33.2 with the hydrogen, and 2.8 is required for compression. So output is this. So 92.2% is the cycle efficiency. Now, if you have the methanol here, hydrogen to methanol, and then you transport. So compression energy for this is around 0.65 for methanol. But here you need to have the CO2 capture also, because that carbon is there. So around 2.02 kilowatt hour per kg of hydrogen is the energy which is required for CO2 capture from the methanol. So the output, if this you look at for methanol, so 5.33 kg of methanol per kg of hydrogen, which is equivalent to this number, will give you around 28.6 kilowatt hour energy. And if you calculate the cycle efficiency here, that is 28.5 divided by the total energy input, hydrogen plus this compression plus this. So this comes out 79.5. Still, this is not bad when you look at the comparison of methanol and hydrogen as an energy carrier. Only thing that your additional carbon capture energy is consumed. Otherwise, methanol can also be used as a source of energy carrier. So the important thing here, when you look at so this is just an example of hydrogen and methanol. There can be several other feedstock and can be compared in the similar fashion. So the conversion efficiency is important, capture efficiency is important, and compression efficiency is important. So that is where one needs to identify the suitable method and then use the best method for the energy carrier. So India has done plenty of this kind of R&D, right? This is the India approach where the biomass, refuse derived fuel can be converted to hydrogen. So at IIT Delhi also we are working for 1 kg hydrogen from this biomass or agricultural residue. So with carbon capture, and then we are looking at carbon production from there. The second one can be a biogas, which is a bio-waste to methane via anaerobic digestion, and that can be a dry reforming here, right? The biogas can be a dry methane plus carbon dioxide. You reform it, or you capture the carbon dioxide and crack the methane, and again you can have carbon and hydrogen. So this is a green hydrogen because this is coming from the renewable sources of biomass. Coal to hydrogen is a question mark, but a lot of things are being done in this area also, right? Natural gas rich hydrogen, or when you talk about the greenhouse, free greenhouse gases free electricity, which is electrolysis, natural gas infrastructure, so by pyrolysis. So these are also the approach where the natural gas rich can be utilized. And you can have to carbon capture here. So that's again, the cost is very important. So when you look at the natural gas infrastructures in terms of grey hydrogen, and then you convert that, approximately this is $1 per kg hydrogen, right? Approximately equivalent to $7.5 per million metric BTU. But if you capture the carbon dioxide, the cost increased by this $1.5 to $1.75 per kg of the hydrogen. So that is, you have to pay for the carbon dioxide capture, but this is the need of the hour, right? So that's what, and there is a potential for this 1.25. You can brought down the cost by this 1.50 to 1.25, right? And you can make it a approximately not a green hydrogen, but green hydrogen. Water electrolysis is still costly. You see that $3 to $5 per kg of hydrogen through the electrolysis, but there needs a lot of R&D, and this can be brought down to a level of again $1 to $2 per kg of hydrogen. And this is again a potential where direct decomposition, and here again $1 per kg of hydrogen or even less, and you have the solid carbon as a product. But this is again the technology which is at R&D level. So I'm not going in detail of this, but a lot of things are to be done when you look at all these fossil derived feedstock and then carbon capture for the utilization, right? So that's a challenge, in fact, when you look at the overall process. So without carbon dioxide capture, around 2.2 tons of methane will deliver 1 ton of hydrogen. That's a simple stoichiometric calculation. And this gives around 6 tons of carbon dioxide, right? So where to take this carbon dioxide, whether you want to take it into the the rocks and all these, right, basalt, what is that technique, or you convert this carbon dioxide into some chemicals, right? You break this carbon dioxide into carbon. So how to utilize that, right? The demand and all these carbons is very important, right? So, and also if you look at this capture of this requires around 5.7 megawatt, 0.41 tons additional methane is required in terms of energy for this capturing carbon dioxide. So that's what overall you see here. There are a lot of processes which need to be done. I'm not going in detail of this. Same thing for the steam methane reforming plus water gas shift and carbon dioxide capture. So those are very important and challenging in terms of the energy. You see here that steam methane reforming plus water gas, right? The heat is to be supplied, the energy is to be supplied, and cost water is to be supplied around 3.3 tons, right? And then you get the around this the carbon dioxide, right, which is released to the greenhouse gas. The carbon is 3.6 is captured, right? Carbon capture and storage, and that gives around 1.1 ton. So these processes needs a lot of development in terms of the carbon dioxide capture. Otherwise, these processes are to be revamped entirely, or some kind of green techniques are to be used. So that is where the steam methane reforming substitute to find out, or the process to be made green. This is where the methane cost, natural gas cost approximately 30 rupees per kg, right? And at 2.2 plus 0.41, which is calculated here, 2.2 tons plus 0.41 ton equivalent. So this is for 2.61 kg per kg of hydrogen. So that means you are paying the extra cost for this, right? So you're right, and this increased the hydrogen cost due to methane alone around 78 rupees per kg. So that is where some kind of energy analysis, exergy analysis and calculation have already been done. And this clearly shows that there is a need to capture the carbon dioxide, but at what cost, right? Whether it is acceptable to the industry. So that's very important. And one has to find out, right? Because every industry have been asked, right, to capture the carbon dioxide. At least 20% they have to use the renewable energy source in order to maintain that, right, the environment. This is again the integrated approach for hydrogen production. So carbon capture, utilization and storage, right? So a lot of R&D is being done in that. And this is the kind of energy analysis which has been done by our group. So you see here that around 40% of low carbon hydrogen supply is linked to carbon capture, utilization, storage, which is the vision for 2070 in the sustainable development. How will it be done, right? You see that fossil fuels, if you take approximately, right, 23 million ton of oil equivalent, right? Then with carbon capture, fossil fuels without carbon capture, this is giving around 17 million ton of oil equivalent, right? In terms of if you look at the hydrogen which is coming, right? Plus this carbon capture. And here, if you have fossil fuels around 87 million tons oil equivalent. So again, fossil fuels with carbon capture, this becomes equivalent to 601 million ton of oil equivalent, and remaining is that carbon dioxide stored is around 1009 million tons, right? So that's a data. Electricity, if you use around 117 million ton of oil equivalent, so all right, when you see around 13,700 terawatt electricity. So this is equivalent to 873 million ton of oil equivalent of the energy. But you see that hydrogen, right, which is generally used, direct use in building, transport, industrial power, around 990 million tons of oil equivalent. Here, ammonia industries around use 133 million ton of oil equivalent, and synthetic hydrocarbon. So this is a kind of speculation when you see the carbon capture and how much equivalent hydrogen will be required in terms of, right, future when you look at the fossil fuel with carbon capture or without carbon capture and electrolysis. So, but this is where you look at in terms of need of the hydrogen in future, and that is required. Similarly, the biomass to hydrogen is again coming up in a green way, right? The biomass to hydrogen is a clean hydrogen basically, or we can call it also blue to turquoise hydrogen, provided the energy which is used by solar energy, right, or wind energy or some other sources, right? Otherwise, this can become totally green also if this biomass is completely life cycle assessment is done and carbon dioxide is captured. So these technologies are also already for coal to hydrogen is well known. But biomass to hydrogen tar is a big problem. So this tar is to be captured, right, by some liquid based absorption techniques or some other method by adsorption, processing adsorption. So a lot of things are being done here. So you see that biomass, and you can have oxy steam blowing biomass. So this is a kind of the technology which where we are working presently. So oxygen and steam you gasify, right, at around 800 degrees centigrade, and you will have the gas. You remove the ash, cool it, absorb the tar, and then there are some kind of the gas cleanup process. So all these are gas cleanup process. I'm not going in detail of this. And then you can have the some water gas shift reaction to tune the hydrogen to CO ratio. So you can have hydrogen here, right, with this. So and that hydrogen can be used, right, by compression and storage. So this is the right R&D where we are looking 1 kg hydrogen per day at our IIT campus using this biomass. So 1 kg of hydrogen can give you around 12 to 15, 1 kg of hydrogen can be produced from 12 to 15 kg of the biomass. It depends on the biomass composition. So mainly cellulose and hemicellulose rich biomass, then only 8 to 9 kg of biomass will be sufficient. If lignin is there, then the amount can go to 20 kg also. So that's a number where rough calculation, and there is a huge potential in terms of biomass gasification or convert this biomass into biocoal, and then coal plus biomass can be gasified in the gasifier. So already with Thermax we are working on this, and that can be used for the hydrogen production. So we have coal to methanol, which is already set up at Thermax, and we are this plant is continuously running for methanol production. So we are using high-ash Indian coal here basically, and this is the what kind of optimized gasifier where oxygen and steam is used as a gasifier. We did lot of hydrodynamic study to design this gasifier, and this is the gas cleanup system. So a lot of impurity, high-ash Indian coal. So the impurities were cleaned up by the gas cleanup island. Then we worked on some catalysis also, and then we worked for CO2 conversion because there are a lot of carbon dioxide is coming. So carbon dioxide to methanol and dimethyl ether. That's a separate project, and this is where the hydrogen can be stored by pressure swing adsorption, and this is a typical blueprint for the hydrogen where 1 ton per day on this. We are also working with GAIL on this carbon dioxide to methanol and dimethyl ether on one of the projects where we are working on this utilization of the carbon dioxide. So there is a huge opportunity when you look at the biomass or Indian grade coal, and this is a kind of already we have already the Department of Science and Technology, and this 1 ton per day of this demonstrable plant is running in Thermax successfully. Lot of things are being done by different researchers on this renewable energy pathways also. This is again a future, right? When you look at the water splitting, or you look at the kind of the sea water, brackish water, although there are a lot of challenges because this is a kind of the quality of the water. So you need to use a kind of the deionized water for this, and then electrolysis, and you can have the green oxygen. You can use this oxygen for some other purpose, and then that will have the green hydrogen, which is 99.9% pure. So that's right. The renewable energy can be used for this purpose, right? And green hydrogen, and this can be converted to ammonia also in the form of to store it, because storage of hydrogen is still a challenge. So either it is a green hydrogen application for oil refinery or all this transportation, heavy transportations, right? Steel plants, gas networks, or green ammonia, then green application like fertilizer, industrial use, energy storage, all these can be used. So that is again a lot of R&D is being done. A lot of things have already been developed by different researchers. So hydrogen from water electrolysis is a challenge, in fact, right? When you look at the efficiency of this in terms of energy, it is totally a green process. But you see here technology, right? The anion exchange membrane technology is being used. Right, the process is which is used. The feed is required pure water at 60 degrees centigrade. The charge carriers are the membranes, anion exchange membranes by electrolysis, so hydroxyl and water. and the product is pure water, hydrogen, right? The power required is more than solid oxide electrolytic fuel cells or SOEC electrical, right? All these kind of the applications can be done SOEC or SOFC to produce the same amount of hydrogen. So generally the differentiator here, if you look at the 4.8 kilowatt hour, right, per normal cubic cube of hydrogen, right, that is the produce output at 35 bar. So that's what and efficiency of this, right? When you see the right hand side, the solid oxide electrolysis, which is done generally the reverse solid oxide fuel cells, right? You can have the steam plus carbon dioxide. You use this for the electrolysis. So you can have green hydrogen, you can have syngas for the FT reactor, you can have ammonia. But this is still at R&D level for the commercial application. Lot of things are to be done. The methods are there, but at the same time, when you compare the process and the cost, that becomes a challenge. You see that hydrogen cost, right? Generally, we target 120 rupees per kg of hydrogen. You see, methane reforming gives around 130 to 250, right? That is the cost of depending on the natural gas, right? In terms of the cost as well as the carbon capture, right? So this is already commercialized technique for the methane reforming. The biomass gasification is generally say you see that 140 to 260. That is again a wide range of this variation in terms of cost. So 1.5 to 4 rupees per kg of the biomass. That is the gasification cost. And this is again still at the proof of concept. The hydrogen yield right from this is I told you that reasonably good in terms of 10 to 20% of the hydrogen which can be obtained from this. The biomass CNG cracking is a cost around 200 plus. And again, this is right a kind of concept, not although methane cracking has been done, but not commercial scale. Most of this CVD have been done for carbon deposition, but methane to hydrogen and cracking with this is still at right. Lot of things are to be done. Coal gasification, again, the hydrogen cost are to 260 rupees per kg, depends again on the coal prices, and this is already commercialized. And here is a hydrogen yield which is 15 to 20. So that's what the low numbers. Bio-oil reforming 250 rupees. So that is again the hydrogen yield is low. Methanol reforming 119 rupees, 95 rupees per kg based on the cost of methanol, and per kg of methanol you see the hydrogen 6.72, that is the yield of hydrogen which can be obtained, and this is also commercialized methanol reforming. Electrolysis is very costly, you see 300 to 500 presently, and that's what has been commercialized, but needs to be right. The cost has to be brought down. So that's very important in terms of the utilization. So these are the couple of new areas, dual bed Syria base, which are not available and just on a concept base for reforming or production of hydrogen. So these are the major methods when you see hydrogen production and cost in terms of energy equivalent. So water, I told you water splitting, which is a high pressure electrolyzer, right? The 55 to 60 kilowatt hour equivalent energy, right? In terms of hydrogen yield per kg of hydrogen that is required here. Steam methane reforming 3 kg of methane per kg of hydrogen. Methane pyrolyzer 4.2 kg of methane per kg of hydrogen. Coal gasification with the highest to 19.2 kg of highest Indian coal per kg of hydrogen. So that's 40% ash I'm talking here. And biomass to biowaste 15 kg biomass per kg of hydrogen. That again depends on the content of liquid. So what I'm saying that I'm not going in details of this. So primary energy cost becomes very important if you see right that. What are the different sources of this water splitting you see at right 3 rupees per kilowatt hour of the energy when you see right here the methane reforming is 18 to 41 rupees per kg of the natural gas. So that is the cost of the energy which is required, and then the things becomes challenging, much more challenging in terms of. So cost of hydrogen when you see if you compare instead of going all this you see that the cost of hydrogen with this water splitting is still 240 to 300 rupees per kg. Compared to methane reforming 200 to 300 rupees per kg. Methane pyrolysis 200 rupees per kg. And this is where the focus is now 120 rupees per kg by coal gasification and carbon capture, coal and biomass. So these could be the options for the India where this can be utilized for production of the green hydrogen, not green, but a kind of the blue hydrogen, right? But you see that carbon dioxide is to be captured. So here no carbon dioxide, but here you have to capture 21 kg of carbon dioxide per kg of this product hydrogen. So that's a problem. Biomass, in one way it is carbon neutral, so it can be utilized as a source of energy. So when you increase this, the cost will decrease. So that's again the right at what levelized cost of hydrogen versus the plant capacity. So that's again the important factor, that how one can utilize these things. So I'm not going in detail when you talk about the unit cost of hydrogen production. That's important here, that the different supply pathways, whether it is steam methane reforming, petroleum coke gasification, the Reliance is doing a lot of work on this petcoke gasification and water gas shift for hydrogen production, coal gasification, biomass gasification. So the production capacity versus, you see that when you have the green hydrogen, no storage, right? You can directly use it for the trucks, rail, ship, or pipelines, you transport it. But if you are using the compression, then all the time you need the energy, right? Whether it is for internal combustion engine, fuel cell, and electricity. So these things, storage, transportation, refueling, utilization, are a big challenge when you look at the hydrogen, right, as a source of energy carrier for transportation purpose. So because most of the time when you produce the hydrogen from these sources, you have to store them either in the cylinder in compressed form, or you have to use the cryogenic condition, but always utilize the cost, right? This is what you see, right? If you are not storing, no cost, but in rest of the cases, if you are compressing, if you are converting to liquid hydrogen, metal hydrides, there is a cost involvement, right? And then it becomes a challenge. Then transportation in the liquid form, compressed form, metal hydride form, right, by trucks. So that is a cost involving factor. By rail, again the cost involvement factor. So that is very important. And when you compress the hydrogen, refuel it, again the cost is involved. So all these are very important and challenging when you look at the hydrogen utilization for transportation or storage and transportation and refueling or any other application, commercial application. Lot of things are being done. You see that transport sector is using, right, the couple of technologies are available, and there are fuel cell electric vehicles, right? So either in the molecular form or the methanol, ammonia, dimethyl ether, and these can be used to operate the fuel cells, right? So that's it. These things, Toyota, Tata Motors, BMW, lot of these kind of fuel cell electric vehicles, hydrogen based electric vehicles are there. There are buses also available, right? And IOCL has also done a lot of R&D on this, and hydrogen plus methane based, what you call hythane, those kind of buses are also available, and which were already planned for Delhi, also in Delhi. So you see here the fuel compression for a car, if you have hydrogen, there is no CO2 compared to gasoline, where there is a 3 kg CO2 per kg fuel, diesel 3.11 kg CO2 per kg fuel, natural gas 2.75 kg CO2. So these are the mileage is also with hydrogen 130 kilometer per kg compared to other fuels, and gram of carbon dioxide, as I said, per kilometer is 0 with hydrogen compared to other. So these are the important points to think where the hydrogen should be used in the future, right? You see that IOCL has this kind of India's first hydrogen and hydrogen CNG station at IOCL Faridabad. They have developed this, right? And this is again a first public hythane, what is hydrogen plus compressed natural gas, hythane, what they call, and that is where the exhaust gas emission, recycle and hydrogen, that synergy can be used, and this will definitely capture the carbon dioxide. So there are a couple of things which are being done in order to utilize the hydrogen, right? And this is the kind of biofuels, like you can have hydrogen plus gasoline hybrid, hydrogen plus diesel type, right? So a couple of these things are available at R&D, and a couple of these things are ready for commercialization. Like this is a commercial hydrogen plus CNG mixture, which is called hythane, and this can be used, right? And when I say methane decomposition, so with 80% methane decomposition also can be mixture, can directly be used for the vehicular application. But online versus offline, these are very important, that how this hydrogen can be compressed, stored and dispersed, right? With proper safety, those are important for the transport sector. So at international level also you see that marine applications, right? So hydrogen based submarines are there, right? So they are replacing the diesel fuel, right? because diesel fuel is very dirty, expensive, but hydrogen can be used as an additive, right? And holds, so this kind of things are, this can also be used to produce power from fuel cell. So these kind of techniques are also being utilized. Then railway also is using hydrogen plus diesel or hydrogen based fuel cells. So these are on trial basis, lithium batteries, right? These are a combination where fuel cell, fuel tanks, hydrogen is stored, then fuel cell generates the electrical energy by combining the hydrogen and oxygen, and that can drive. So it has around 625 plus miles, right? This kind of train which you see here, right? In the IC electric traction motor based, and these are the references one can go through this. So this is not being done in India, but globally in the world, these things have already been done. So as in the beginning, it was said that, right, how to address the challenges of hydrogen storage. So a couple of R&Ds have been done, like mechanical storage. So hydrogen needs to be compressed at high pressure, like 700 bars, and you can store it, right? So those kind of storage devices are there. Tanks design and pumping system need to be specifically designed for hydrogen. High pressure means higher compression. So this is being done, but at R&D level, and couple of, say, like Air Product have developed couple of hydrogen storage tank also. The storage material is very important. So lightweight materials, composite materials, these are the need of the hour, right? Which can be used, right? Because the corrosion-free vessels are required. The lightweight materials are required because they say like at least 6 kg of hydrogen is to be stored, right? Whether under pressure or cryogenic condition, which will drive around 350 miles, 500 kilometers. So that's what the target. And after that, you can refuel it, right? That can be cryogenic liquid storage tanks also, like right under cryogenic condition. So liquefaction of hydrogen, that will be required -253 degrees centigrade. So what kind of material will be used here? So those are again the challenge, right? So energy penalty equivalent to 25 to 30%, right? Equivalent to 10% of natural gas of the initial quantity of hydrogen. So these are the challenges which needs to be addressed, right? For storing and transporting hydrogen. So a lot of things are being done at R&D level. How can we store the hydrogen? Physical storage like compressed gas, cold or cryogenic, liquid hydrogen, or you have material based, like lot of R&D is being done in this area as an adsorbent, as a liquid organic, interstitial hydride, metal hydrides, complex hydride, chemical hydrogen. So all these are being used, right? And but as I said, that 6% is the requirement of storage. These materials have 3 to 4% so far. So that's again a challenge. So where how to increase this number, make it a level of 4 to 6%, so that the driver can run it at a minimum of 500 kilometers before recharging these kind of or replacing these kind of adsorbent. So a lot of things are at R&D level. A metal organic framework, chemical organic framework are coming up in a big way to work on that. So transportation can be done, as I said, by road, by train, by sea, by pipeline, but these are still, because the hydrogen cryogenic condition is a very brittle, right? And you need to look at that, how that temperature -200 degrees centigrade or 254 degrees centigrade temperature, or very high pressure like 700 bar. So how to handle those kind of, right, situations when transporting the large amount of hydrogen, right, by these materials. So these are the major challenges when you talk about green hydrogen economy, right? So safety, hydrogen safety, because it's a high flame speed, right? Wide flammability limit of hydrogen, right? Need extra safe approach for handling. So these are the challenges when you look at the development of technology for utilization of hydrogen as a clean carrier. Simultaneously, these safety aspects should also be studied. So a lot of things are to be done, and very limited study have been done so far on safety of hydrogen related disaster mitigation with regard to its handling. So industries have to come forward for this, right? No research has been done on long-term adverse health effect on people or animals in case of chronic or persistent exposure of hydrogen. So that is also, right, yet to be identified. In future, when you look at, right, scale up, there will be associated waste generation and management will be highly critical. So that is also just like when we're talking about electrolyzers, right? Then they need to be salvaged, right? Their life is limited, right? Batteries, right? Fuel cells, right? Solar panels. So their life is limited. So what is when you look at cradle to grave concept, that is also to be simultaneously analyzed, right? So those kind of devices, their life and how to handle them in future, right, when they are being discarded. So there are a lot of things which needs to be done. So I'm not going in details of this, but a lot of things are being done in order to produce the green hydrogen, like renewable electricity, right? Water electrolysis. These are at R&D level. BARC has done a lot of work on this, right? Water electrolysis, and a lot of things are being done, right? Solar, wind, hybrid-based commercial electrolysis, right? Based hydrogen cost for India, which can be about 150 to 40 per kg of hydrogen. That's what the target, but presently it is very costly. Then green hydrogen using biomass, biowaste, as I said, we are also working at IIT Delhi and looking at target of 120 rupees per kg. So decentralized versus when you talk about biomass, right, the waste which can be generated in decentralized manners, how this can be transported to from one point to another, and then how can be say whether it is biomass to hydrogen or biogas transportation and then use it. So a lot of things are right, the points to be discussed, right, in order to develop this hydrogen based technology in India. So these are a couple of, right, you see that India is doing a lot of work. So this is the work which we are doing. BHEL is also working on this. SIMFAR is also working on the similar approach. So a couple of these, right, coal to methanol based technologies, and that has given a direction on coal to hydrogen. So methanol can be reformed or water gas can be reformed, and you can have hydrogen, capture the carbon dioxide, and that is where we are looking with a target, right? This can be utilized for fuel cell application. So there are the right 1.5 megawatt plant on India highest coal gasification, that is the Thermax is doing at Pune, right? And we develop 1 TPD methanol plant, and that is where you need to find out the cheaper renewable energy and clean fossil made, right? Hydrogen based, right? Energy storage, carriage, energy control. So these are the R&D level work, but the national mission program on this hydrogen, coal gasification, methanol, right, and hydrogen as a source, ammonia. So these are to be done for the future if you are really looking a carbon neutral society in 2070. So just at the end, because of the paucity of time, I am just closing it here. So India needs to carve its own pathway for renewable fuels, right? And this should be a kind of blend of hydrogen, which includes carbon dioxide capture and fuel cell based, right? All these kind of vehicles which can be used. So if you look at this, if you use this, then we need to target 25 million ton of hydrogen production by end of this decade. That is important because that is the demand, as I told you, right? 6 million ton will rise to 25 million tons, right? So 25 million ton hydrogen, if you are thinking, this means 75 million tons of the crude oil equivalent. That is to be, right? And 25 million ton of this hydrogen equivalent to 100 gigawatt of electric equivalent. So that's what we are just calculating the numbers, right? And 25 million tons, if you are able to produce hydrogen, 8 million tons of this carbon dioxide can be captured or saved. That's what, if you are using hydrogen, 25 million. And that should be the beginning, right, in order to initiate this process. And at this point, right, if this can come from equally from renewable biomass, coal, or natural gas, and this is need to be developed, right, for the discussions required. Lot of things are to be done, right? So we need to develop a kind of demonstrable units, right? Whether it's a GAIL or Ministry of Petroleum and Natural Gas, or right PCRA or coal, Ministry of Coal. So these organizations have to come forward to look at these kind of demonstrable units, right? Or a combined effort should be made. And decentralized manufacturing and consumption can eliminate or reduce the transportation and energy storage challenge. So that is again important. Injection of excess hydrogen into existing natural gas lines will result in hethane, the mixture. This can also be used, right? And refineries have to come forward, like IOCL has done that. Essential to capture the carbon dioxide, right, and from coal and biomass. So this is important. Gasifiers need to be integrated with carbon capture and utilization to produce blue hydrogen. Economics need to be ascertained before fixing the location, and that's what overall we need to develop a net zero carbon by end of 2070. So with this, thank you very much for providing me the opportunity, and if there are the questions, I'll be happy to answer.
Thank you, sir. Thank you for such a beautiful and an excellent. Thank you for sharing your knowledge on the efforts that are being taken, the opportunities that are available in the market, and the challenges that we have towards the growth of hydrogen economy in the country. We would now open the house for any question answer, for a brief question answer session. So we'll take up questions from here and then go for the chat box.
Yeah. Thank you, Professor Pant, for giving an excellent presentation and touching upon almost all the aspects related to hydrogen, be it the technology or the affordability, connectivity, transportation, utilization, what are the customers, where it will be produced, how it will be sold. So there are various aspects which do come up when we have to move to hydrogen-based economy, so to say. And direction is set to go into that transition already by various ministries from the government of India. So if there are certain questions, we can take it up, or
So I can read out the question.
yeah, you can
Please.
We have a couple of questions. Mr. S.C. Sinha wants to know, sir, the question is.
I think let me read the chat box. So the first question is what percentage of fuel, petrol plus diesel, is expected to be saved in coming 10 years by using hydrogen as an alternative fuels vehicle? See, actually the target, as I said, right, 25 million ton of hydrogen equivalent, which I have given by end of this decades, right? And if you do that, see, the total demand cannot be completed, but at least we are looking a phase down, right? So we are looking 20% of this, like methanol, we have said 20% of methanol, and gradually we'll go with 80% methanol, then 100% methanol. So these are a phase wise. So at least 20% of this hydrogen, right, it can be from the green energy sources. This will be a huge asset in terms of the carbon capture. And gradually we have to look at the number, because once you have a small scale success, then gradually with over the years, this can, because vision is 2070 zero carbon. So gradually we have to take it to the exponential level. So approximately 20% would be sufficient in the beginning, because production of this green hydrogen will be a huge challenge as far as the economy is concerned. So that's the low cost hydrogen is very important. Then the second question is that kindly elaborate more on biomass gasification process. Actually, biomass gasification is a known technology. See, there are two ways. One thing is you can pyrolyze the biomass and convert it into bio-oil and then reform the bio-oil. Both options are possible. Bio-oil reforming will give you hydrogen, right? And then capture the carbon dioxide. Second thing is the biomass gasification, similar to coal gasification, right? The only thing that coal gasification is simpler in terms of the tar. Biomass tar is little bit complicated, right? Because it has a lot of polyphenolic compounds. So those can be cracked further. So that's what in our oxy steam gasification, we have done this coal plus biomass gasification. And now we are targeting this 1 kg hydrogen in IIT campus itself with the support from the different industries and Department of Science and Technology, that agricultural residue can be gasified around 850 degrees centigrade. And then we are capturing the carbon dioxide, and then that carbon dioxide is again being used, carbon dioxide hydrogenation, to methanol and dimethyl ether. And part of this carbon hydrogen will be utilized. So in total, if you look at low carbon emission and net cycle, that's a challenging, because hydrogen for CO2 hydrogenation itself will require hydrogen. So CO2 hydrogenation thermodynamically very rigid, and there will be cost which is involved for hydrogenation of CO2. So whether CO2 is to be hydrogenized or CO2 is to be broken by plasma cracking to carbon only. So that could be the options where we are working on. But this is the biomass gasification is just right, and then you reform it. So water gas set reform you do after that. So you can have high hydrogen and carbon dioxide. You can have biomass gasification for syngas and syngas to methanol also. That is the similar technique which we have done with the coal to gas. Then the third question is, what are the limitations of using hydrogen as a fuel? I think I have already discussed that. Lot of the safety aspects are there, right? And then transportation. So fuel cell is one of the options by which the hydrogen can be. So 1 kilowatt, 5 kilowatt fuel cell reformers, onboard reformers are also there. But so far the hydrogen directly as a fuel is little bit difficult because of the safety aspects and the kind of material of construction, as well as the storage at high pressure or cryogenic condition are the challenges. But hydrogen is being used already. Then the question is, what is the water requirement to produce hydrogen with electrolysis? This simple equation, if you write H2O gives H2 plus half O2. So 18 kg of water can give you 4 kg of hydrogen. So that's but provided the efficiency 100%, right? So the efficiency is not 100%. There are a lot of losses. So that's what the challenge. Otherwise, mass balance wise, 18 kg H2O gives you H2 plus half O2. And Then what is the calorific value of hydrogen? So calorific value of hydrogen is 120 megajoule per kg, right? So which I have given there also. So 120 megajoule per kg is the calorific value of hydrogen. Yeah, thank you, Dr. Singla. We would like to meet you and discuss, right? So whenever you are free, please visit IIT Delhi campus. Then there is a question again from Mr. Singla. Hythane mixture contains percentage of hydrogen. Actually, this is a little bit varying. Generally, see, low hydrogen and high methane is hythane. So 10 to 15% is the hydrogen and remaining is the methane, which is in hythane. But gradually this percentage has to be increased. This is what I was talking then, because if you are moving towards hydrogen based vehicles, then this methane compress, because your carbon dioxide emission is more in the hythane. So if you want to move to zero carbon, then gradually you have to increase the hydrogen percentage and reduce the methane percentage. Then keeping in view of storage limitation, how long it will take for hydrogen to become, right, one instance choice for fuel for private vehicles. This is very difficult to answer at this point but I think if there is a vision, if there is a motivation, and if the plans are done accordingly, I think all these energy companies sooner I think we will be able to come to that level. But presently it is very difficult to state this point. How long will it take hydrogen to become? I think Dr. Ashu would be able to answer this question. Or so.
So, Professor, I would like to ask one question, that there is a lot of technical research is going on that how much hydrogen can be blended in gas network. But we have not yet found a solution across the globe that somebody is saying, and there's no regulation as of now. So there are people trying in Europe to go up to 20% blending, and there are regulation in Netherlands up to 1% of blending. In India, we are going up to 1% or 2% we have allowed in city gas network. Now, my question is that in Japan, they have been using hydrogen since quite some time in fuel cell and other applications. So why no regulation, or what are the main constraints that hydrogen cannot be mixed in high pressure gas pipeline? What are the major issues related to it, in your view?
Yeah, I think it is a brittle hydrogen corrodes, the brittleness of this, right? The pipe becomes brittle. This is what I observed, right? And I was discussing this with Professor R.K. Malhotra also earlier. So the transportation of hydrogen under cryogenic condition would be very difficult. So because these say minus 250 degrees centigrade, such a cryogenic pipelines, right? This will become brittle. So your pipeline will get cracked. So that's a one problem. If you use the cryogenic hydrogen, this is what I feel. And if you have a high pressure, so high pressure hydrogen, say 220 bar, all these cylinders are also available for hydrogen, 220 to 700 bars. The carbon based carbon filament lightweight material, those kind of tanks have been developed for hydrogen storage. So for transportation purpose, that is good for vehicular application. But if you want to transport the hydrogen from long distance, right, for refinery application from source to the end users, then there is a challenge. So still, I think there are a lot of things on hydrogen storage and transportation has become. Japan have developed, see, fuel cell vehicles are already, say, 1 kilowatt reformers, as I said, methanol based as a carrier. These are easy to handle. So 5 kilowatt reformers, 1 kilowatt methanol based reformer, these are already been developed. The natural gas based, there are a lot of R&Ds have been done and lot of technology are available also, where you have methane and then use it in the plate type reformer, generate the hydrogen, and that hydrogen can be used in a fuel cell application or vehicular application. So it means how much natural gas will be required, right, and then transport it into fuel, but the carbon dioxide capture in between the cycle is important. Then you have a green hydrogen process which can be used for this vehicular application. But I think the Japan has developed a couple of technology. India is also working on fuel cell. Lot of R&D has been done, but the cost is a challenge as of today.
Yeah, but just one more clarification on this is that existing pipeline network of gas pipelines, which is of maybe X60 grade or X80 grade. So can hydrogen be blended in those networks also?
No, I don't think so. I don't think.
What are the main problems associated with it?
Brittleness, actually brittleness, and then see hydrogen is a gas, right? And properties of hydrogen are different than the natural gas. So when you look at the pressure in the line, so natural gas liquids, hydrogen, and so there will be, I think, lot of issues in terms of two-phase fluid transportation. So it will be a two-phase, and that will also have the problem in terms of fraction losses in the line. But details, I too have to study those parts.
Okay, so that is fine.
But there are a lot of challenges when you look at the hydrogen plus natural gas transportation.
Now you have given a target of, means say targets to reach up to 25 million ton by 2030. Currently we are at 6 million tons. So I mean, it's a good target, it's ambitious also, but the main problem will be one that it is very costly as of now. If we use green hydrogen, which is actually totally environmental friendly. The other option is if we use electricity from the grid and use electrolysis to produce hydrogen, then the carbon footprint will be still high because we are using coal almost 70% in the grid mixture. So in a transient phase, that will not be a very good solution.
I agree. I fully agree with you. Actually, this is a kind of speculation where we need to work for this, right? Say, so whether it is a hydrogen from biomass or if it is hydrogen from coal gasification along with carbon capture, right? And then simultaneously the transportation. So whether you use it for the electric grid purpose, just like ammonia is also, right, one of the options instead of hydrogen. So that could be a green hydrogen. But with when you look at the power grids, right, unless it is the solar, wind, then the issues will always be there. And the cost is very important, which is challenging.
Anybody from any other questions?
Are there any other questions from the in-house participants here?
One more, please.
But I have a question that India is going for the hydrogen national mission, the national hydrogen mission, but still the technology. So
Yeah, I am not. Can you clear your voice?
Can you talk closer to this mic?
Spider.
Dr. Pant, my question is that India is going for the national hydrogen mission, and we have many things to do. But from your presentation or from the other studies, it seems that the real technology to harness or to produce hydrogen is still not established or cost effective. So how we can go about to achieve the targets in the national hydrogen mission? Like that?
No, I think, see, we should not say that it's still not effective. The only thing, the water electrolysis has not come to that level. So it means we need to find out, right, when you look at the entire energy balance. So now people are doing the process intensification at the end, observing the losses and minimize the losses. As I said, the fuel cell efficiency, 60% can be reached, taken to a level of 75% efficiency. If that can be done, the cost will come down. Biomass to hydrogen, I told you, it can come at a cost of 120 rupees per kg, right? Coal to hydrogen, again, say coal to methanol, we are already working to a level of 25 rupees per liter of methanol. So I think the only thing that you have to run the plant with proper energy analysis. So exergy analysis is another catchy term which is being done. So if you are measure the losses in the plant and try to utilize those losses, capture those losses, and then use it again in the process, then efficiency will become increasing. The cost is going down because the process plants are not running up to the efficient levels, right? Just like coal gasification. Coal gasification efficiency, if the combustion efficiency 90 plus, then the cost will go down. But presently the coal combustion efficiency itself is 70, 75. So lot of unburned coal is coming back. So those things are important. So I think a proper energy balance will definitely bring the cost down, and that is where need of the hour. Electrolysis of water also, the targeted solar water electrolysis, there are the methods by which the MNRE is doing a lot of work on those areas, right? So solar water electrolysis will bring down the cost of this water electrolysis hydrogen. So that should be done.
My question was that, I mean, the cost is still very high, so we cannot use it commercially.
No, no,
At
no,
the-
no.
at the-
No, 120 rupees per kg of hydrogen when you are comparing, right, with say 300 to 500 rupees per kg of hydrogen, right? And then obviously, see, when you look at the cost of carbon capture, because if you are using methane reforming and the carbon dioxide is there, you have to capture the carbon dioxide. Otherwise, you have to pay the tax for that. So if you are able to connect this cost of carbon dioxide capture with the methane stream reforming, that is definitely equivalent to what you are getting from this other sources. And one has to do that.
Okay. One
Because
more
for
question is
carbon
that,
neutral society, the cost of carbon dioxide capture is to be done.
one small question also, that you said that the hydrogen blended in natural gas, transportation of blended hydrogen in natural gas is not very advisable in existing pipelines, steel pipelines.
Long
So
distance
it is-
pipeline, long distance, short distance, the hydrogen is already being used.
So is it better to have dedicated hydrogen pipeline for
Yes,
transportation?
actually design is required. Proper design for hydrogen based pipeline is required. Because if you are using cryogenic or high pressure, the material of construction is very important.
Good afternoon, Dr. Sir. My question is that is there any effort to change the pipeline material for better uses of hydrogen? Because I understand Netherlands is a low temperature country, so their environment and our environment is completely different. And being hydrogen is a so light material, so there is always a. I understand there's for if we use P63, P80, or P100. There is a chance of leakage, loss of hydrogen. So is there any effort to address these issues?
Yeah, composite carbon based materials are being used, right? People are working on this, or these pipelines with composite materials are being tested, where the diffusion, as I said, under pressure, this problem will be more. But if it is under cryogenic condition, the problem will be less. So composite materials are being designed for the gaseous hydrogen versus liquid hydrogen transportation and storage.
But you have just mentioned that for cryogenic, there is an issue of brittleness.
Yeah, then
So
if it is
both
cryogenic,
are
then
to be.
issue. No, but this composite carbon based material, they have good strength, just like stainless steel, or much better than that. So these carbon composite materials are being developed.
Okay, okay, sir. Thank you.
But not through the pipeline, for storage, not through the pipeline transportation.
So thank you, sir. Thank you for making the session so very interactive and sharing the entire knowledge and the database that you had with you. And with that, we'll conclude this session. But before we come to the last leg of the session, I would request Dr. R.S. Wilmurugan to formally deliver the vote of thanks for the session.
Professor K.K. Pant, our Executive Directors, Sri Asu Singalji and Sri S.K. Gulyani-ji. A very warm good morning, and good morning to all the participants connected here through physically present here and also virtually and also through YouTube channel from the PCRA. This is the awareness program on the occasion of SAKSHAM 2022 on behalf of GAIL team and also team GTA. I express my gratitude to all the esteemed members of PCRA, MOPNG for entrusting GAIL with the responsibility of conducting this awareness program and session on part of SAKSHAM 2022. We are also delighted to be part of the nation building in this new hydrogen economy. I thank the eminent speaker, Professor K.K. Pant, for sharing and sparing his valuable time with us and your nice presentation starting from the green hydrogen economy and how it has gone, various technologies, and also what are the challenges. Thanks, sir. It's a very deep presentation. We thank you for such kind of presentation. I also extend my thanks to all the attendees present, our participants present here for their time and keep this knowledge with them. Our special gratitude to our ED Asu Singalji, He highlighted the national hydrogen policy, and our ED SK Gulyanaji is in charge of this GAIL Training Institute to take out their time, grace the occasion, and encouraging us for conducting this program. Finally, I thank the team TQM department, BAS department, and also GTA team, acknowledging their efforts in coordinating and organizing this event. Thank you, sir. Thanks to all.
Thank you for providing me the opportunity. I really enjoyed the discussion. Thank you very much.
Thank
Yes,
you.
sir.
Thank you, sir.
Now I request BIS team to end the event here. And sir, we'll get back to you by end of day today.
Thank you very much, sir.
Okay, thank you. Thank you.
Disconnect.
Disconnect.